Hello everyone, welcome back. Today we are going to look at lecture 3 of building small language model from scratch, and we will continue from where we left off on the code walk for our small language model. And this is the session where we are going to do these last 4 steps. We're going to define a loss function and then set up the training configuration for our small language model, and then use the language model architecture class that we have built and pre-train this small language model with the data sets that we have from steps 1 to 3. And once the pre-training is complete, we will provide sample tokens, sample sentences, and see what are the predicted token values. Initially, for the live demo, I'm going to probably train this language model for about 10-15 iterations, and just to make sure we follow how these 4 steps work, and then once the initial training is done, we can go into a larger set of iterations. So let me jump back Colab, and this is our implementation of the transformer architecture, which we went through in great detail, line by line, in the code walk. One piece which I had left out in the previous lecture was this part where with no gradient calculation. So this is part of our language model architecture. I'll quickly walk through what is in this piece of code, right? So while this piece of this code is specifically utilized when we have to generate tokens. So as you can see from this input, here we are specifically telling that there is no need to actually calculate the gradient and do the back propagation and all that. When we call this function, we are going to primarily pass in this these two, where this is the initial set of tokens that we are, the sentence that we are giving, and then the max number of new tokens that needs to be generated, right? So we are going to loop over this max number of new tokens that is needed. And as you can see here, what is happening here is we are taking the input, we are taking this input here and just making sure that the input is not greater than the block size. In our small language model, we set it as 128. So if the sentence that we give is got more than 128 tokens, it's going to take the last 128 tokens and then send that into the model. So this line is sending that into the model and getting the logits out. So when we do this, the forward pass would happen and the logits will be returned, which will be having the shape of batch, number of tokens, and the vocab size, right? And we are only interested in the last token, right? So that's because we want to see what, given a sentence, what is the next token that gets predicted, and which is why we are going to then take the last token that comes out of it. Okay, and of course there's division by temperature control for the sharpness and things like that, and then we apply softmax on that logits to actually get the next token. And once we get the next token, we add that into the input. Now that is concatenated and attached to IDX. So that's what this goes through in a loop, so that each time we will get the next token up till the maximum number of new tokens that we need to capture. So that is this piece of the code generate, where we are using the trained model to generate the next tokens up to the number of tokens that we need. This is on the trained model. Now we looked at this code where we created the model with the configurations, and then this is how we instantiated the model class, and with the configurations that we have for the small language model, we went through all the parameters and how each of these parameter weights are initialized, and the comparison between our small language model and GPT-3, which had 173 billion parameters. Now, let's pause a moment to understand the loss function. Essentially, this is just for us to see how well our model is performing. As we run through a whole lot of iterations, then as these parameters are getting updated, how do we really see whether the model is converging, and if our loss is optimized, right? So that's where we use this estimate loss function, right? It calculates both on the training and validation for the model at whatever state it is trained for a fixed number of iterations. It will evaluate the losses, and then provide us the value. So that way we can see, is the losses average loss going down, right? It's a very simple method. So we put the model itself in an evaluation mode. So this way we can disable a lot of the gradient calculations and such, and it just to calculate the losses, it operates fast. And then we run it twice, one for training and validation. And for the number of iterations we wanted to evaluate, we go in, get a batch, the get batch, where we are going to get into training or validation.bin file, and from the file we'll get our 32, 128 and all our 384 dimension inputs, and what should be the output. And then we evaluate that in the model to get the logits and the losses. Here we are interested in capturing the losses, and we'll get the mean of the losses, right? And as you can see here from this loop and the way this is arranged, we are going to, till the number of evaluation iterations, we are going to pick batches and run it through the model, and can calculate and add it to this losses variable. And then once we come out of it, we are going to get the mean of it, and which is what is returned. And then we will put the model, when we do this estimation of losses, we are going to put it in eval mode. When we are going to come out of it, we should remember to set it from back to the training mode from the evaluation mode, and that's what gets returned out. So that's the definition of this. This is how this loss function is calculated. So with those two aspects out of the way, let us look at what are the training configuration, right? So it's pretty much we've done all the coding that is needed for defining our whole model class, and also how to generate the tokens out of it, as well as how to estimate the loss function. So that's pretty much all the code that is needed. Next, we need to go into see what are the configurations, right? Understand how these configurations, because these configurations are what will essentially determine how we run the training on the model, right? This is the actual execution. So here, this is some parameters. Since typically, this, depending on the amount of GPU you have, this number can be really high, and this is dependent on the data set as well. So for the free tier, I think the max iteration indicates the total number of epochs or iterations, and I'm going to do in the final training. I'm going to do that over 20,000 iterations. If you're on the free tier, you could do it up to 4,500, because after that, I think Google typically, I think you run out of resources or your quota for the free tier, and then you have to come back the following day. So that's why the max iterations, right now I set it at 100 because I want to give you a live demo of how this happens, right? And then evaluation iterations. So right now I set it at 5, typically set at 500 when I'm running it separately. So what is this? Evaluate iterations is like, say if you're running it for 20,000 iterations, you want to, like, at every 500 iterations evaluate the loss function, like is your loss converging or it's going high, right? And the next important parameter that we want to set is this learning rate, right? So this is the when we are doing the after the gradient calculation and we are updating the weight parameters, what is the step size that we have to use, right? And when as we are training the language model, so if you consider this 1 by e to the power minus 4, assuming, I mean, e is 2.712, so this would be roughly 0.185. Again, these are hyperparameters that engineers and scientists have identified. I'm just borrowing those values here. And as we are, I mean, one more aspect in this setting this learning rate is during the initial steps. In this case, if you're going to run this iteration for 20,000 times, the initial warm-ups could be for 1,000, right? So this would be where running here you would kind of keep the learning rate minimum for these 1,000 steps, and then little increase the learning rate and updating the weights with a higher value, right? And the minimum that it can go is 5 e to the power minus 4, which is 0.09, right? Like that. These are hyperparameters that we are setting. Another important step that you would need to know, another important configuration is this gradient accumulation step. This is really the number at which you want to have the back propagation happen and have these learning rates applied on the weights because you don't want to do it during every single iteration, right? So that is the gradient accumulation step. Device, definitely CUDA is best if you're using CPU. Frankly, it is not going to be possible to run this, right? Like on the free tier. So so these are some of the typical configurations. There's also a second part 2 to the configuration. Let's see what's on here. So this is how the model weights would be updated, right? We talked about the learning rate. There's more details in it, how the learning rates are updated, right? And that is if you look at this, and that's through the learning rate scheduler, right? And there are different types that we are importing from it, right? Essentially, the most common and popular one is this Adam optimizer, right? Which is very popular. And I think we are initializing this Adam optimizer here and passing on our learning rates, and also some parameters here. The weight decays if there are large weights and helping them prevent overfitting. So we're initializing that, and then a small value if the denominator doesn't become 0. So those are some initializing we are doing for the optimizer. And during warm-up, we will implement linear warm-up, and then after the warm-up, the learning rate can be further reduced to follow a cosine curve, and that's where this cosine enabling learning algorithms come in. So essentially, after that, we combine our scheduler to have these sequential as well as the scheduler decay, the cosine learning rate optimizers added. So now I wouldn't go detail into this. There's a lot of mathematics and more understanding that needs to happen. But for the purpose of this course, I think we're good to understand that these are all the configurations and hyperparameters that need to be set before we go ahead and pre-train our small language model. So the code walk for the to pre-train the small language model, that is here. It's actually pretty simple code, right? Just a few lines, and I'll walk through the code before actually starting to execute it. So as you can see, we are just defining a model, best model params name, and then if you already have a model that you want to train a little bit more, then you can of course load that model here and then continue to train it. What we are doing here is we want to for the max number of iterations, be it 20,000 or 4,500 or just for the live one like 100 iterations. So we want to loop through it, and if we are getting where we want to evaluate the losses, like in this case we chose 500, or if you chose a value 5, then if that is reached, we want to go in and calculate the losses, and then print out for training and validation data set what it is. And also we are trying to capture the optimizer, what is the learning rate at that point, right? Like how far, by what value the weights are getting updated. And then we are just appending the training validation loss into a list so that we can graph it out at a later point. These two lines are important because if we are seeing that the losses that we are receiving is less than the best value loss, then this is an improvement on the model. So we want to assign the new value as the best value loss, and then we want to save that into this file, best model params path file, which will basically physically store the weights value, the latest value, as we update them with the learning rate during back propagation, right? So this is basically the first part where you're evaluating and saving the model params, and this is where we are really getting the batch right. So for every iteration, if you can see, we come here, we get the first batch that we want to train, and out here we are calling the model. So at this point our model class gets called and the forward function gets executed, and it returns back the logits and the loss values, and then we are with the losses, we are first we are calculating the gradients of the loss with respect to model parameters. And then as we our gradient accumulation step, as we reach that 32, I think here we initialized it to 32. As we reach that number, we are then going in and uh, uh, essentially asking the optimizer to update the model parameters. And then also, once the model parameters, that is all the weights, are updated with whatever is the learning rate, we would reset the gradients of the model parameters to 0, right? And so that way we can again go back and with the new batch once again train and go through this cycle. So we are not accumulating gradients continuously, but are able to optimize it. So those are the theory. Now I've done something simple here, so it's easy for me to go live. I'll right now I just switch this to CPU environment. I'll change it back to the TPU. Why I wanted to do this is just to show how this training is happening. So I really put a very small value of 100, and this way I know, like I've set the max iteration as 100, and where did I update it? I think it's in the out here. So I said max iterations as 100 and every 5 iterations to evaluate it. And I let it run on a CPU because that way it is actively running and you can see the progress very, very easily, right? So as you can see here, we are in the 47th iteration of the maximum 100 iterations, and every 5 iterations we are calculating, and that's this part of the code, right? Like evaluation iteration is 5, and max iterations I set as 100, and I've given it a CPU, so this goes very slowly. As you can see here, you have a training loss of 10.8 and validation loss of 10.83, and then the current learning rate is really small, right? And then so next, it's at the 10th iteration again we've calculated it, we've applied this learning rate to change the parameters training loss. So this is what has is happening in the training part. Now what I'm going to do is stop the training at this point, and then switch it to the GPU environment, and then run our training. What I'm going to then do is, once the pre-training is complete, load that model and then give it some sample sentences and see what the output is. The way we will do this is, I'll train it for like 100 iterations, let this one complete, and then train it for 4,500 iterations. Let's see how it looks. And then as we improve the number of iterations and our model gets trained and it converges more, we will look at what the how the response is, and whether we are training it on a whole lot of text of short stories that's that can be read by probably 4 or 5 year old. And let's see, based on that training, when we give simple sentences, is our small language model able to provide coherent, readable sentences in English. Okay, so I'll pause there and be right back. Okay, this is why you should never use a CPU to train a small language model. Nevertheless, for demonstration purposes, for the 100 iterations, it has taken 56 minutes. So you can see how after every 5 iterations you have a training loss and validation loss computed. and there we go. So the learning rate has been very small. So from the initialized model parameters, the updates would have been really small. Now let's do something very simple. Yeah, this is the plot of all the validation loss and training loss for each of those steps. It, as you can see, even though the learning rate is very small, it is steadily going down and converging, right? Um, but let's look at now let's look at trying to generate the output for the model which is trained just for 100 iterations. So that is the step. We are initializing the model, and we have only CPU. We're using the model which has been trained for 100 iterations, and we're just loading that into the state dictionary. Now with that loaded, here is a sample sentence we have. Once upon a time there was a pumpkin, and then we are encoding that sentence here, and then using our generate model with for this sentence, and we are saying generate the next 200 tokens for me, right? And what's going to happen is when we invoke this is going to go back and call the we have loaded the model, and it will go back and call this part in the model class, the generate. Okay, so let's see what it looks like. If there's going to be a lot of gibberish that comes out. Now since I am on a CPU, it's gonna take a really long time in spite of being in spite of all the gradients being off and such. So this is what it is like. If I can just copy the cell output, now I just copied that in here. So for iterations 10 with evaluation with a max iteration of 100 and evaluation every 5 iterations, this is what it is. We get once upon a time there was a pumpkin, and we get some totally not understandable nevertheless tokens which are I mean it doesn't make any sense at all, right? So we really need this model, for which I'm going to switch over to TPUs, and what I'm going to do is probably take it up a notch, but not the whole 220,000 iterations. I'm going to do a max iteration of 4,500. Since this is on the free tier, this is a safe one, so it doesn't disconnect, and I'm going to run it with this number, 4,500 iterations at least, and with evaluating every 500 iterations. Let's see what we get. And this is what my training response was for 4,500 and iterations at 500 evaluated every 500 iterations. On the TPU, it still took 44 minutes for me. You can see the training losses declined a lot more rapidly, right? And the learning rate after that initial 1,000 iterations stepped up high steadily. I think that's probably the cosine factor coming in. And here is what we were looking for, right? Once upon a time there was a pumpkin, And now it says, once upon a time there was a pumpkin. She running. She had a magical tree, thief her birthday and book. She woke himself one of her house help. She must spots on her wrong. So it's still not coherent. Doesn't make a whole lot of sense. But a far cry, lot of improvements that we are seeing compared to what we saw here, which not even one word made sense in this sequence. But this one definitely um, is a lot better. Now, I'm confident that as I go up to 20,000 iterations, 30,000 iterations, this small language model uh, can generate a lot more coherent sentence with more training. So that's what I would do. And I'll see you once I run a lot more of these iterations, and we'll be back after